Let's we'll finish the edge detection today, then corner detection. Okay. Let me summarize very quickly for what you have learned last week for edge detection. As I mentioned, for edge detection, we can apply either the first derivative, okay, then we measure the magnitude because the edges is based on the transaction of the intensity between neighboring pixels, okay, or we can apply the second derivative, and by identify the changes of the sign, but for practical implementation, we still use the magnitude. 我说我们不看它的正负值，还是看它的直接看它的量，那个差异量。Okay, no matter the differences from the second derivative or second derivative, okay, we simply use the magnitude and compare the magnitude with threshold. Okay, so last week you have learned because we are talking about the two-dimensional image, so that we use the gradient, okay, the gradient instead of the derivative. No matter what, you need to take the derivative with respect to the x-axis and y-axis, okay, separately. Okay, that's what you have learned. So the commonly used operator, okay, can be a preweight, okay. This is to identify the vertical edges, and this is another mask or filter to identify the horizontal edges. And then this is the most popular one, okay, called SOBO operator. That's the name you got to remember when you apply it with any computer vision software, okay. Or if you want to have the same responses, okay, in the horizontal, vertical, and diagonal edges, then you can apply channel-free operator, but keep that in mind because the elements, okay, in each filter, they are not integer, okay, so it means the computation time could be longer. When I say longer, it's not actually very long, okay. It's just relatively long compared with the integer-based SOBO operator. Okay, and if you want to have a very thin edges, you can go for 2x2 rubbers. Okay, 2x2. This is the smallest, okay, filter for edge detection. Okay. Okay. And then the second derivative usually we simply based on Laplacian, okay, based on Laplacian. This is a 3x3 Laplacian operator, okay. In the middle you have a positive, okay, -4, and in the four neighbors you have a +1, or inversely left one, okay. You change the sign. It doesn't matter, okay? Okay, we show this example. And this is another 3x3 Laplacian, okay? In the middle, you have the value of A. In the 8 neighbors, you have a -1, okay? The summation is 1 again, okay? It's 0, I'm sorry, okay? Okay, and I talked about this is a so-called compound filter. A compound because this filter can apply for smoothing to remove noise. And it can also be used to identify the edges. Okay, that's so-called compound. 我们叫复合式的滤波器。也就是说，它一次可以做2件事情，同一个滤波器，一个呢可以做平滑 ，because Gaussian itself is a smoothing filter. Okay, but when we take the derivative of the Gaussian, then we can apply that for edge detection. So it means that the derivative called DOG. Okay, DOG. And this is the filter. Okay, this is the filter, which means what? The user, you can design your own filter. 你说你可以设计你自己的哦。This is the filter, and for the user, you need to set up the window size. Okay, you need to determine the window size or the filter size, and then the bandwidth. Okay. For this case is sigma. Okay. This is the user. You need have to define it, and not xy. Xy is given. Okay. The filter is given. What is given? In the middle. Okay. For a 3x3 in the middle, which means you input 0, 0. Okay. To this equation. For the element that will have the coordinate -1 for x. Okay, for this case here, xy equal to -1 and 0. Then you put -1 and 0 into this equation, and you come up with the result and put the value here. Okay, that's how we design the filter. You know what I'm saying? Okay. Of course, you can use OpenCV. Okay, then find the derivative of Gaussian or LOG. Okay, but anyway, this is the filter. This is the filter. It has 2 parameters. One is the window size. One is the bandwidth. Okay, the larger the window size and also the larger the bandwidth, you will have better smoothing. You can remove a lot of noise, but also you will blur the edges. Okay, you will make edges. The width. It cannot get a fine edges with a very large filter size and bandwidth. Okay, and also we talked about another compound filter based on the second derivative is so-called Laplacian of Gaussian, which means we take this the first derivative of Gaussian, then we take another derivative. Okay, or anyway, we take the second derivative of the Gaussian, the so-called Laplacian of Gaussian. Okay, and the filter is given by this equation here. Okay, this is the filter. Okay, this is the filter. Again, for the user, you need to define what should be the window size of the filter and also the bandwidth. So you put the bandwidth here. Okay. Well, usually you can drop this term, okay? It's nothing but a scale. You can drop this term. Even you have a parameter sigma here, but it's okay. The sign is given. It is given by this, okay? This equation, as I mentioned last week. Okay, this term actually is a circle, right? It's a circle, okay? And the other parameter is the bandwidth. Okay, and Sy again. The central coordinate of the filter will have x equal to 0, y equal to 0, and then you know all the remaining value for s and y. Okay, they don't need to be determined by the user. Okay, 所以说这个，你说这个就是它的滤波器哦，要记住，这个就是它的。So you can design your own LOG, okay, Laplacian of Gaussian. Okay, simply define your own window size and the bandwidth. Okay, and all the x, y, the coordinate value is given by this notation here. Okay, anyway, the coordinate value in the center will have x equal to 0 and y equal to 0 also, and all others. You will be clear. If you go for 5x5, okay, for example, you go for 5x5, then the value will be -2, 0. Then you put -2 and 0 into this equation here. Then you will then you will have the output log. Okay. But today, the final thing about edge detection, the final thing we need to discuss is the so-called canny edge detector. It's so famous, okay, in the computer vision field. That's something you need to know. But you got to remember the canny, okay, the name, okay. That's something you need, even you forgot how it works, but somehow you need to remember so when you use OpenCV or any software, computer vision software, you need to search for the name, okay, Kenny. Kenny is the author who developed this algorithm, okay? Now, for Kenny edge detection, it need to go for 3 steps. First, it do the Gaussian smoothing. It do the Gaussian smoothing first. Okay, and then I should put 1, 2. Then you do the edge detection. Okay, or you calculate the edge magnitude. Okay. Now the most important thing is, I should not say most important thing, but that's the only. I mean, it's nothing for the step 1 and step 2, right? Okay, you can apply Sobel operator, right? Then you apply a Gaussian filter for smoothing, then apply a Sobel. Now, the long maxima let me show you. Let me just show you the image first, okay? Actually, you saw this. Okay, this is the original input. This is the result of soap operator. If you apply rubbers, you can see a much thinner, okay? Much thinner edges. And this is the result of canny detection. You can see the width of the edges is almost only 1 pixel more, okay? The reason for that, it will getting clear, especially by, let me show you here, by this operation called non-maximal suppression, okay? Non-maximal suppression, I will explain. Non-maximal suppression, we suppress the edges and to make it thick, and how to make it work. Well, actually, you can, if you know something about the edge detection with deep learning, you can see. We will get into that. Okay, that before. If you want to find a pedestrian, an edge detection, it might give you here's a person or a pedestrian, but it will also say you might have another bounding box or a bounding box like this. It won't show you a single bounding box. So if you show you 3 bounding boxes, you might say, oh, there's 3 pedestrian. No, it's not true. But around this pedestrian, it will give you a very strong evidence for an object you are looking for. So you need to go for the non-maximal suppression, which means it just retains the one that will return the maximum value. That's it. Okay. I mean, it's nothing to do. It's nothing to do with the edge detection, but this is some kind of operation by just retain the maximum response. Then when you say non-maximum, it means if something didn't return the local maximum value, then we suppress it, which means we remove it. OK， 也就是说，它们在附近都会有很强的反应。I mean, it say a lot of. If we got an edge that will respond like this, then we do the so-called non-maximum suppression. And after that, we might just retain only the, okay? We have a thin edges. That's why we can have something, detailed edges, okay? So let me go back to talk about how it works, okay? But anyway, basically you need to go through these 3 steps. Well, actually that's you will have, because the maximum suppression, let me show you the example again. Actually, I mentioned that there's the result from the cutting edge detection. See that in the curve, some of the curve, I mean the edges are broken. They are broken. That's because when you go for the non-maximum suppression, a lot of fine detailed edges is removed. And then we need to do something to put it back, okay, to put it back. That's the last thing, okay. I should not say connect the broken edges, but I will show you, okay. Method connection, okay. Anyway, that's basic. And the main operation is right here, okay, non-maximum suppression. But in case you forget all the details procedure, something you need to keep in mind is you need to know what are the parameters that you need, okay? Otherwise, when you apply OpenCV, you don't know what should be the right parameter. Or you simply just use the default, but the default value won't give you the best result for your application, okay? 所以假如说都忘了整个程序没关系，至少你要记住的是它的参数指的是什么。You must remember what should be the parameter, okay? So that you can input or you can change the parameter value instead of just simply use the default value given by OpenCV or any computer vision software. Okay, so let's go back to see how it works. Okay, the cutting edge detection. So first, let f of x, y be the input image. Okay, we are talking about the ground level image. Okay, ground level image. Then we apply a Gaussian filter. Okay, you remember what I just mentioned, what Gaussian filter is, right? Okay, you can apply Gaussian filter with an appropriate smoothing parameter, the bandwidth. Okay, find your bandwidth. I will show you example later on. And then we calculate the gradient magnitude, okay, from the smooth image, not the original image, okay? And then the gradient magnitude, then we apply, for example, the Sobel operator. We calculate the gradient in the x-axis and gradient in the y-axis. So then we calculate the magnitude, okay, the magnitude, the length of the vector, okay? So we call it m, okay? M means magnitude, okay? And then, as I mentioned, whenever we talk about the gradient in a two-dimensional image, we're talking about a vector, okay? A gradient is a vector. First, you can calculate the length or the magnitude of the vector. The other thing is we can calculate the gradient orientation. 第一个，它既然把它当向量 okay? Because the vector, because we have a gx and gy, okay? Then this is the gradient direction. Okay, we simply taking the inverse of tangent gy over gx. Okay, then you can calculate sigma. Okay, anyway, sigma can be defined between 0 and 180 degrees or plus minus 90 degrees. It's up to you. Okay, but anyway, we care only about the degrees between 0 and 180, okay, with 0 to 2 pi. Okay, the procedure here. So first, we do the convolution, okay, we go with the filter, okay, go with the Gaussian filter. The convolution, I already defined what is the convolution, right? For each point, okay, we do the convolution, okay, in the neighborhood between, for elements or pixels x and with coordinate I and j, okay, which is defined in the filter. 这个没问题了哈，我们就做选基映射 okay, the convolution. Okay, then f hat is the smooth image. And then we apply the gradient operator, as I just mentioned. Most of the case we use Sobol operator, a 3x3. Okay, we use a 3x3 operator. Of course, you can use Roberts. Okay, and at the meantime, we not just calculate the magnitude, we also calculate the gradient direction. Okay, so let me give you an example. So first, we may have a Sobol operator, for example, the Sobol image, like this. Then we calculate, well, I should make it a little bit thick, okay? This could be all H's. Then I calculate the gradient, okay, the gradient. What is the gradient here? For this point, this is the gradient direction. This is the gradient direction. This is the H direction. This is the H. This is the H direction. But for this one, this is the gradient direction. Okay? What about the point here? This is the gradient. Okay? Because the gradient direction must always orthogonal with respect to the H direction. 也就是说 H 的方向跟 gradient 的方向一定要正交两个是正交的 Okay, and this, okay, this is the direction, and this will be the direction, and again this will be the direction. Okay, and for this one the direction could be 45 degrees, right? And the direction here could be 0 degree, right? Okay, you know one thing, right? Okay. Okay, so here's how we define the direction. The direction, as I just mentioned, okay, is calculated by G1 over Gx. Then we take the arctangent, okay? Then we calculate the theta. Theta can be defined between 0 and 180 degrees or plus minus 90 degrees, okay? Why we need that? Then for this example here, we have an H's. This is the H. And then this will be the gradient direction. Okay? And assumedly, we will have the magnitude, suppose the magnitude will distributed just like this, right? In the middle, we have a large magnitude. But when you're getting far away from the middle, then the magnitude will become smaller. That's the idea. That's so-called, we do the non-maximal suppression, which means we retain only the local H point with a maximal magnitude, and we remove all others. Okay, so here's the procedure. Okay, suppose because we simply assume that we use a 3x3, just a 3x3, then we only have a 4 direction. Okay, we have a 0 degree, 45 degree, okay, 90 degree, and 135 degree. Okay, so for us, this is the so-called 0 degree. And for this one, it's 45, this is 45 degree. Okay, and for the point here, that will be 90 degree. And for the point here, we have 135 degree. And then we look for, we define its neighbor. Okay, if the gradient direction is 0, then we look for its neighbor, two neighbor. One is with 1, 0, minus 1. It means what? Okay, we have this. Okay, for any h, x, y, and the theta value is 0, then its two neighbor will be minus 1, 0, 1, 0. Okay, everyone follow me? This is the coordinate difference of the two neighbors. Okay, so if theta equal to 0 degree, and we have x, y here, so its two neighbor will be what? X minus 1 and 0. Everyone follow me? Why is it minus 1? That's because we put minus 1 here. Okay? And what about the coordinate? Then it will be x plus 1 and 0. Okay? I'm sorry.
It's y.
Should y, not 0. Okay, I'm sorry. This is coordinate. And then we calculate m and put m here. M is what? The gradient at this location. Okay? And also the gradient at this location with Sobel operator, for example. And then we compare the magnitude of these three. If fxy, okay, is not a maximum, it's not a local maximum, then we remove this point so that we can shrink, okay, or reduce the width of the edges. Okay, that's the idea. Okay, so but I just put it 0, 1, 2, and 3. Okay, as the pointer. So it's 0 degree. Its two neighbor is defined by these two coordinates. Okay, and it's 45 degree. It's 45 degree. Then its two neighbor will be along. So that's why you see. So you can see something here. Okay, so if this is the h direction, and this will be the gradient direction. Okay, so that's how we define its two neighbors. If theta equal to 45, okay, if it equal to 90 degree, then we look for its two neighbors with the coordinate shift 0, minus 1, and 0, and 1. That's it. Okay, that's something. Fortunately, you don't need to write your own canny edge detection, but that's how it works. Okay. So if you want to know more detail, that's how we determine these. You should use 0. Okay, 0. The pointer should be 0, 1, 2, or 3. That's how it works. Okay. Now let's say that it is calculated by the gradient direction. Okay, because the resolution for 3 by 3, because the resolution is 45 degrees, so we plus 25, 22.5. It means what? If all the value, okay, between less than 45 degree, less than 45 degree, it will return 0. You know what I'm saying? Okay, 这是所有的值只要小于45度的答案 because it plus 25.5 divided by 45. Then we take the integer. Then the value will not be okay. So it becomes 0, 1, 2, or 3. That's it. Okay. That's just some practical programming. Okay. You can think of any better way, but that's how we define it. Okay. So anything between for any point, we plus 25, 22.5 and divided by everything less than 45, then we will return 0. Okay? Everything larger than 45, then you will larger than 45 and between here, okay, then you will return what? 1. Okay, you know what I'm saying, right? Okay, that's the resolution. That's because we only think of a 3 by 3 direction, okay? So anyway, then say if f the magnitude f xy is less than its neighbor, okay? That's what I put as the neighbor. Say that's the parameter, okay? That means x minus 1 and y. If theta equal to 0. If this magnitude is less than its left neighbor or right neighbor, then we set m of xy equal to 0, which means we don't think of it as an h. That's it. That's so-called non-maximal suppression. 就是它跟它的2个周边的值比，然后呢，它假如没有比它周边的值更大，我们就视为0 which means we remove these edges. Okay? And how to set up its neighbor point is just by look for this table. Okay? And the coordinate, the pointer should be 0, 1, 2, or 3 is simply given by this, okay, transformation. Theta is the gradient direction. And we plus 22.5 is because the resolution for A direction is 45 degrees, okay? So everything is less than 45. We think of it as to be 0, okay? Which means all the value in this range will return 0, okay? And all the value between 45, okay, and 45 plus 25.5, then you will return 1, okay? You will return 1. Okay, so that's so-called the non-maximal suppression. Any question? Okay, up to now, we don't need any parameter, okay? Or what you need is, the only thing you need is the Gaussian filter, okay? You need to determine, as I just mentioned, you need to determine what should be the filter size, okay? In most of the cases, we simply use a 3 by 3, but it doesn't matter. You can define your own Gaussian filter. Okay, the second one should be what? Should be the bandwidth, okay, the bandwidth. Okay, that's for the user part in new setup. And for the non-maximal suppression, you don't need to do anything, okay? You know, there's no parameter. But after that, we need to do some, then finally, we go for the edge detection, okay? This is the usual way for the user. You need to, there's two thresholds. You need to set up the threshold, okay, for the magnitude. If the magnitude, of course, you can apply also thresholding again, just like what you have done in assignment number 1, or you can determine manually based on some primary experience. Anyway, basically you need two threshold, okay? T means threshold, H means high threshold, and the other one called low threshold, okay? You will set up. But usually we simply set, for the user's part, you need to set up only the high threshold. And in the original paper or most of the programming code, the low threshold, we take it to be half of the high threshold. So in that case, the user only have to specify the threshold, okay? Or you can determine it automatically with also thresholding. Okay, then as I mentioned, after you do the non-maximal suppression, a lot of quite a few edges will become broken, okay? It will become broken. Now, this is the last part. You will put it back, okay? Try to make the connection again, okay? The fourth part. We will try to connect, okay? The neighboring edge point, okay? Here's how you do it, okay? First, if we have a edge point up to the non-maximal suppression, If we think of xy is an edge, okay, with a mark of 1, okay, 1 for edge point, 0 for the non-edge point or the background, okay. So if xy is an edge point, then we look for its neighbor, okay, its neighbor. Here's we use a neighbor rule, okay. We just look for its neighbor, okay. If all its neighbor has the value larger than the lower threshold, think of it, okay. We will put TL. L means lower threshold, okay. So if we set up the high threshold to be, so first we check for fxy at coordinate xy. If fxy larger, the user specify high threshold, for example 90, then you will look for its neighbor. And any of its neighbor have the magnitude larger than half of the high threshold, then we change its mark to be 1, which means we want to put it back, okay? So it means after the maximum suppression, you might have something like this. And then when we check for this one, then we'll think of its neighbor, okay? If the magnitude is still quite large in terms of the lower threshold, then we will turn it into 1. As you know, when you develop the algorithm. Do you think the author, the original author, will come up with this process? Definitely no. It will stop here. But you found out what? You have a lot of broken edges. So it adds something more, okay, to bring it back. What I'm saying is when you do your own research for your thesis or when you work for a company and working on computer vision, you will always do something good, but you will find out there's some pitfall. Okay, and then you need to add a more procedure to overcome this problem. So from the procedure here, actually you can see, okay, there's some good idea. The author Kenny think of we work for edge detection from the original image is not better than this from the smooth image, and then try to make the edges, okay. Try to get some fine edges by non-maximal suppression, but after that we can reduce the width of the edges, but somehow you also have the disadvantage with broken edges. This the final step it proposed to make them connected, but it's no guarantee, okay? It will fully connected, but anyway, that's the idea, okay? So this is the procedure for Kenny edge detection. Any question? So for the author, okay, for the author, the first one you need to determine this could be the filter size, okay, and the bandwidth, which is the signal, okay. And it's fine for non-maximal suppression because it retains only the local maximum. Okay, we don't need any threshold. But when you try to connect the neighboring, we need what? We need the high threshold and also the low threshold. Okay. But as I mentioned, most of the time you need, for the user, okay, for the user, you only have to specify the high threshold, okay? And the low threshold is simply set to half of the high threshold, okay, to make the thing easier, okay? So when you apply the Kenny edge detection, you need to specify, this is especially for the bandwidth, okay? The bandwidth and the threshold. Okay, so let's take a look at one of the example. Okay, we already talked about this. Okay, you can see a very fine edges, but some of the edges or the segment, okay, they are not connected, especially in the corner. Okay. Okay, you can see something like this. Okay, and here's another example. Okay, this is the original image. Now, the first, let's take a look at the effect of the Gaussian smoothing parameter. Okay, so first the sigma. Okay, the bandwidth for Gaussian smoothing is a very small 0.5. Okay, and the high threshold is set at 90. Okay, and low threshold is only half of the high threshold, which is 45. Okay, now this is the original image. Okay, and this is the smooth image, and this is the detected edges. So you can see there's quite a few noise point here. Okay. Well, actually, I want you to put more attention on the chimney. Okay. Actually, you can imagine there should be an edges, right, for the chimney. 那个烟囱应该会有一个and visually we should have an edges here, right. But just by looking at the smooth image, you cannot see anything actually. But after the threshold, after the detect edges, you can see a lot of noise here. But somehow all this noise is set up the edges, right, for this one. Okay, for this one, just something like this. You might have an edge. When you take a look, this should be, okay, if this is the chimney, right, then you will see something, this part here, okay, that's the good thing. It will give you some fine detail, but also it creates a lot of noise. Now, if we increase the bandwidth to be 1.4 from 0.5, and see that, you can see that most of the noise is gone. But however, you cannot find the edges, right? It shows the evidence there's edges for this chimney. Okay. Now, if we increase this, we didn't change anything about the high threshold, okay, and low threshold. But if we increase the bandwidth from 1.4 to 7, see that? Now, it's very clear, right? Contains no noise. And it shows only about the most important edges of the house, right? Okay, so it is still quite important when you apply the canny edge detection. You need to keep in mind what is the most important thing for this application, right? Do you need to preserve or to identify the details of the edges, or you try to remove the noise as much as possible? Then you should go for this one to determine the filter size, or especially about the bandwidth. And then later on, you need to determine what should be the high threshold. Okay, high threshold. That's it. Okay. If you have no idea, again, you can use what you have learned from assignment number 1. You can go for the author's method to set up this threshold automatically and set up half of this high threshold as the low threshold to make a connection. Okay. Okay, let's about the canny edge detection. Okay, a very famous one, and for the researchers. In this field, it is well known. Okay, you can get a fine edges, especially when we talk about Hopf transform. Okay, not today, probably next week. The Hopf transform, because for Hopf transform, we don't care if the edges are broken or not. It won't be affected. Okay, 好，这晚一点我们在谈那个霍夫转换的时候 ，OK， 我不用关心那个线是不是断掉啊，所以。在很多应用呢，它断不断我们不关心，可是我们关心是什么？它要越细腻越好。Okay, this canny edge detection. Okay, then next topic will be the corner detection, okay? Why we need to talk about the, now, try to remember how we define edges. The edges define what? The intensity, a significant intensity transaction, right? In the neighboring pixel. Now, how are you going to define the corner? If you look for the dictionary, okay, you cannot find any, or mathematically, there's no way you can define corner. You know what I'm saying? But when I say corner, you know what I mean, right? You always know what I mean by corner. But mathematically, how you define the corner? How? It's a tough question, right? I mean, if you have an edge like this, I'd say this is a corner. You have 5 corners, okay? Every one of you will agree with me, right? Right? But if you have something like this, then what should be the corner? Well, this got to be a corner. This could be a corner. No, is this a corner? It could. Or it should. It have the corner, right? However, if this is a corner, then this got to be a corner. And this is corner. What about it? What about it? If this is a corner, then this will be the corner, and this will be the corner, and this could be also the corner. You know what I'm saying? I mean, so if say, we don't need this, this could be just a noise. Okay, if this is a noise, then this will be the noise. It's very difficult. Okay, mathematically, you can only define the corner what? The intersection point of 2 non-parallel lines. 两条非平行线的交点就叫 corner， 大家都可以同意。But for this one, we don't have 2 non-parallel straight line, so then it will be very difficult. But anyway, the one thing we know is what? The corner point got to be an edge point. Which means what? Because the corner detection could be very time consuming, okay, to calculate. So when you want to identify a corner point from an image, the first thing you need to do is what? To identify the edges first. To identify the edges first. Because a corner point got to be an edge point. Because it's very easy, okay, relatively easy to identify the edges. And next, you just make sure this edge point is also a corner point. That's it. But don't try to find corner point from the original image pixel by pixel. That will be very time consuming. Okay? So first, always remember when you go for the corner detection, always try to find edges first, and then check each individual edges as a corner or not. Okay, so next I will talk about how we define corner. Okay, how we define corner. It is also very important features, like if we have an image here, once you have this fine corner point, you can define the object, right? We just need 5 points to define a complete object, okay, as simple as a pentagon. Okay, let's take a look.